This is lecture outline 10, starting with page 4. We just did on pages 1 to 3 our first complete Lewis structure, so let's do a couple more examples. One of the examples we're going to do is C2H4. C2H4, we have 2 carbons. Each carbon has 4 valence electrons. We have 4 hydrogens, each one has 1 valence electron. So we have a total of 12 valence electrons to put into our Lewis structure. Now we talked about how hydrogen cannot be a center atom. One thing that's a little strange about having 2 carbons in a molecule is that they do tend to be connected to each other and then have the H's around them. And we will see that's a general trend that is not covered. Most of the molecules and ions that we will see have 1 central atom, but if there's more than 1 carbon, start by hooking those carbons together, at least for Chem 1010. Okay, so just by connecting our carbons and our hydrogens, we have 2, 4, 6, 8, 10 electrons. We have 2 more to put in for a total of 12. We can't put them on the H's because the H, it only wants 2 valence electrons, the same as helium, and it has 2 valence electrons. So we put them on one of the carbons. We're not sure which one, so we just choose one, and then we see that the other carbon does not have an octet. So we take a pair of electrons from the carbon that has an octet, share it with the carbon next door, and we end up with our final Lewis structure for C2H4. Another common one that we will do, H2O. We have 2 times 1 plus 6 valence electrons for the 1 oxygen. We have 8 valence electrons. Put the oxygen in the center. Can't have hydrogens. And then by the time we complete the octet, we have used up all 8 of our valence electrons. What we will see is that if we look at the 4 most common elements, and we're going to make a little table here, and the typical number of bonds, that there are some general trends, some definite general trends. For example, for a carbon, we're going to have typically 4 bonds. And we can go beyond typical. We're going to say almost always. It would be, we will see a couple cases, including at least one on the homework where there's a different number, but that'll be very strange to us. Hydrogen, again, we can go beyond typical. It has 1 bond always. There's no exceptions to this that I can think of in Chem 1010. Even Chem 1020, maybe OChem, I don't know, we'll see. Or you will see, or somebody will see, not me. CHO, here we'll get to typically. Typically it does have 2 bonds. We can see that in water, oxygen has 2 bonds, and 2 what we'll call lone pairs, or non-bonding pairs of electrons. Nitrogen typically will have 3, and so 2 and 3, those are typical numbers. We will see many cases where they're different than that actually, but you are generally, so you're going to get used to seeing mostly 2 bonds and mostly 3 bonds for oxygen and nitrogen. And on the next page we're going to talk about something called formal charge, and I just want to put in a word about this. These typical or almost always or always numbers of bonds are representative when these elements have 0 formal charge. These elements have 0 formal charge. With these numbers of bonds. Okay, and again, we'll talk about that on the next slide, where we talk about formal charge. Formal charge, capital F, capital C will be our abbreviation for it, is a hypothetical charge on an atom assuming that all bonding electrons are shared equally between the two bonded atoms. There will be an equation for this. Formal charge equals the number of valence electrons from the periodic table number of valence electrons from the periodic table. By that I mean the number of valence electrons we would use to come up with, or we would assign from for a Lewis structure. For example, carbon and all the elements in this column have 4 valence electrons. Fluorine, chlorine, bromine, iodine have 7 valence electrons. So from an atom, say, that's another way to say it, but from the numbers from the periodic table. Then we're going to subtract off, and here we're going to subtract off 2 things, so we'll put them both. The first thing is the number of bonds, and the number of unshared electrons. Number of unshared electrons, and note, we oftentimes think of electrons in pairs, but we're going to count each electron separately. And then we'll put this. So you're going to take formal charge is the number of valence electrons from the periodic table minus the sum of these 2 quantities. And let's go ahead and see what this looks like for carbonate, the one we've already done. If you remember the valence or the Lewis structure for carbonate, it has 1 carbon-oxygen double bond and 2 carbon-oxygen single bonds. And typically it has square brackets around it if you're going to not do formal charge analysis, but we will, and we'll see that we're going to actually position the charges in the Lewis structure here, as we'll see. So I won't put the brackets for this one. And you should know that you will always do formal charge analysis in Chem 1010. So just get used to it. And you'll see I ask for it on the homework, the recitation. All right, so here's formal charge analysis. We'll start with the carbon. Formal charge on carbon. Carbon from the periodic table has 4 valence electrons. And from there, it has number of bonds is 4. Number of unshared electrons, well, there are 0 unshared electrons. So 4 minus 4 is 0. And carbon has 0 formal charge. That will always be the case when there are 4 bonds. Now, for oxygen, we're going to have formal charge on oxygen, what we're going to call oxygen A. And oxygen A is going to be the oxygens that have 1 bond and 3 pairs of electrons or 6 unshared electrons. So I'm going to put orbital A next to both of those. From the periodic table, oxygen always has 6 valence electrons. There's 1 bond and 1, 2, 3, 4, 5, 6 unshared electrons, so same for both of these oxygens. 6 minus 7 is minus 1. And so what that means is these 2 oxygens, each of them has a minus 1 formal charge. And the way in which you show a formal charge is you put a minus sign and you circle it. So a minus sign with a for a formal charge has a circle around it. And as long as you put the minus sign somewhere where you can tell which atom it relates to, it's fine. It doesn't have to be far down in the corner here, but just so long as it's clear which atom the formal charge is associated with. Now, we also have an oxygen that we'll call oxygen B. Come on back there. There's my O. 6 valence electrons from the periodic table. This time we have 2 bonds and 1, 2, 3, 4 unshared electrons. 6 minus 6 is 0, and so we have a 0 formal charge. On any atom that has 0 formal charge, there is nothing to write. On any atom that has a non-zero formal charge, from now on you will want to note that, as we have. And if you do, and when you do, you don't need the square brackets that we did in the last one. So we won't be seeing square brackets on anything else that we do because we're noting formal charges. Okay. All right, that is our formal charge analysis. And now let's do some more examples of Lewis structures, then formal charge analysis. After we talk about rules for writing the best Lewis structure. And we will always be writing the best Lewis structure, so we will always be doing formal charge analysis. The most likely Lewis structure has the fewest atoms with non-zero formal charges, or the most atoms with 0 formal charges. So that's the first thing we want to do. And then the next thing is negative formal charges. Negative formal charges are more likely to be on more electronegative elements, so we'll need to know our trends in electronegativity. Now let's write the best Lewis structure for thiocyanate ion. Our process will always be this. Write the Lewis structure with octets, do a formal charge analysis, and then do what we need to do to minimize formal charge over and over again. Rinse and repeat, as they say. So SCN minus, so sulfur from the periodic table has 6 valence electrons, carbon 4, nitrogen 5. We have a negative charge there. Add 1 electron. There are 16 electrons that we have to put into our Lewis structure. All right, come on. There we go. 16 valence electrons. Carbon is the least electronegative. It will go in the center. Connect the atoms by single bonds. Sprinkle your electrons around the outside until each of them has an octet, or 8. And we have 8 plus 8. We have 16 valence electrons, and carbon in the center only has 4. So this time, one approach is going to be to do 2 double bonds. Because the first thing we always do is we always make sure everybody has an octet. Then we think about formal charge. So everybody has an octet, 8, 8, 8. Now let's do a formal charge analysis on this. Formal charge on carbon, so 4 valence electrons from the periodic table. Then 1, 2, 3, 4 bonds, 0 unshared electrons, formal charge of 0. Anytime you see carbon with 4 bonds, which you're almost always going to see, formal charge is 0. Now let's talk about this sulfur. 6 electrons from the periodic table, same group as oxygen. 2 bonds, 1, 2, 3, 4 unshared electrons, 0. Now at this point, so I'm going to tell you that the formal charges on the atoms have to add up to the overall charge on the ion, in this case, or molecule. So formal charge must add up. So formal charge must add up to the overall charge on molecule or ion. So that's a hint that this is going to be -1. Then the other hint comes from, well, if you look at the periodic table, there are 5 valence electrons from its position on the periodic table. There are 2 bonds, 1, 2, 3, 4, unshared electrons, -1. So we note that with a minus right there. Now, you don't ever have to do this, meaning you don't have to show your work for these. You can do it in your head eventually. You can show your work, but you don't have to, as long as you show non-zero formal charges on final Lewis structures. Now, there's another case here where we could have done something like this. Instead of doing a 2 double bonds, we could have done a triple bond here. And a single bond between the sulfur and the carbon. We still have 8 valence electrons for nitrogen, 8 valence electrons for carbon, and 8 valence electrons for the sulfur. I apologize that this keeps losing focus here. We'll work on that. But now let's do a formal charge analysis. We'll do it a little more quickly this time. We have carbon, 4 bonds, 0 formal charge. Nitrogen, 5 valence electrons from the periodic table. Then 1, 2, 3, 4, 5, 3 bonds and 2 lone electrons, 0 formal charge here. Sulfur, 6 valence electrons from the periodic table, -1, 2, 3, 4, 5, 6, 7. We end up with a -1 there. And then the question becomes, okay, so both of these finished Lewis structures have the fewest atoms with non-zero formal charges, but then the negative formal charge must be on the more electronegative atom. So which is more electronegative, sulfur or nitrogen? And you wouldn't necessarily know this unless you had the values, and you will on your third exam on the final. Turns out nitrogen is more electronegative. And therefore, this is the best Lewis structure. And oftentimes, well, we'll see. We'll get a feel for when we need to do formal charge. And if this were the case that I wanted you to look at, I would have to ask you to look at it. Because generally, we would want to form 2 double bonds before a triple bond. This one's going to be a blank page, page 7. We're going to do a couple more examples where we do Lewis structures with formal charge analyses and show you just a couple strange things, perhaps. The first one we're going to do here is the Lewis structure and then formal charge analysis for nitrate. Nitrate, a very common ion. We're going to do, let's see, 5 plus 3 times 6 plus 1. We have 24 electrons. And we have 2, 4, 6 electrons in here so far. 8, 10, 12, 14, 16, 18, 20, 22, 24. We don't have enough valence electrons to complete the octet on the nitrogen. That means we have to do a double bond. Now, that is the finished Lewis structure for nitrate. And now let's do a formal charge analysis. We see oxygen with 2 bonds. Oxygen with 2 bonds is going to have a formal charge of 0. Oxygen with 1 bond and 6 electrons is going to have a negative formal charge. And nitrogen, 5 valence electrons, 1, 2, 3, 4 bonds, no unshared electrons, that nitrogen has a plus formal charge. And that is a lot of formal charge, but that is the best we can do. Everybody has their octets. There's nothing else to do. This is our best answer. Negative formal charges are on oxygens. Positive, which is more electronegative than nitrogen. Nitrogen being less electronegative, is our center atom. Let's do another example. Let's do H3O plus. We have 3 for the 3 hydrogens, 6 for the oxygen. A positive charge means take 1 electron away. We end up with 8 electrons. Hydrogens cannot be in the middle, so oxygen has to be in the middle. And finish it out, we have 8 electrons, and they're all around oxygen. Now we have 3 bonds for oxygen and 2, so 6 minus 1, 2, 3, 4, 5. We have a positive formal charge oxygen, which is part of the H3O plus Lewis structure. Hopefully you're getting an idea that you're following the steps for the Lewis structure. You must memorize them. You must come up with a system that always gets you a Lewis structure with all of the atoms having 8 valence electrons, satisfying the octet rule. The octet rule rules! And then we do formal charge analyses. And we find all the formal charges, and the formal charges must add up to the overall charge on the ion. And usually that's just 1 if it's a +1 or a -1, but sometimes there's more. Let's see. Oh, another interesting case, carbon monoxide. Carbon monoxide, we have 4 + 6, that's 10 electrons, 10 valence electrons. Connect them by single bonds. Sprinkle your electrons around. Two, 4, 6, 8, 10. Now, each of these atoms is missing 2 electrons. Neither of them has an octet. You do end up with a triple bond here, and 1 lone pair on each atom. When we do a formal charge analysis, formal charge on carbon looks a little weird. Carbon does not have 4 bonds. Formal charge will not be 0. Formal charge here for this carbon, 4 valence electrons from the periodic table. 1, 2, 3, 4, 5. 4 minus 5 minus 1. Oxygen, 6 valence electrons minus 1, 2, 3, 4, 5 plus 1. There's an overall charge of 0 in this molecule. However, there is formal charge in the molecule. These are some strange cases, and I wanted to show them to you because the process always works. You always get a Lewis structure if you follow the steps. Then you do a formal charge analysis, and you see what that formal charge analysis tells you. And it's oftentimes something interesting.